the fun thing about what we're going to talk about today, again, the things we talk about, we are just going at a very surface level clip, try to give you a little idea of some of the different aspects of math, maybe some of the different ways it's used. So one of the uses of modular arithmetic is in writing codes, meaning codes to keep things secret. So if you want to make an ID number or something like that, like what's the pattern? How do you make things like that? So we're going to start with or basically most of these are going to be simple types of what's called a check digit. We'll look at a real world example of UPC codes that you see when you go to the store, and everything as a UPC code is a good use of modular arithmetic. Okay, so here we go. Let's look at example 1. That's where we're going to start. Example 1 says this. Suppose I got a 4-digit code, and it's created for each person in a group so that the 4th digit is assigned to make the sum of all 4 digits divisible by 8. So this is kind of the simplest idea of how you would make a code that's kind of unique to you, and you give everybody in your club one, and you know if somebody made one up because you do the quick check and it's not divisible by 8. And so we're also given the idea that the digits 0 through 8 can be used. Okay, so remember, divisible by 8 means that the number divides evenly by 8. Another way to say that, and the relevance to this to modular arithmetic, is if something's divisible by 8, that means it's congruent to 0. It's in the same congruence class as 0. There's no remainder. Okay, so it's congruent to 0 mod 8. Okay, that's kind of the crossover to why this supplement is given at this point in the class. So here's what we're going to do. This first problem, we are going to make sure, we're just going to say, okay, somebody has the code 7125. I want to know, is this a valid code? Why or why not? So the rules for this are the sum of all 4 digits are divisible by 8. So the way that I'm going to check is I'm going to say, okay, 7 plus 1 plus 2 plus 5, that's going to be the sum of the digits. So when I pop that into my calculator, 7 plus 1 is 8, plus 2 is 10, plus 5 is 15. Is 15 divisible by 8? No. When I divide 15 by 8, I'm going to get a remainder. In fact, the remainder is 7. Here's the mathematical symbol. You can write right now, if you want, 15 is not divisible by 8. But if you want to be mathematical and impress your friends and family members, then here's how you write not divisible by. So this bar right here, if I wanted to write a number was divisible by 8, I would write 15, I'd write a bar like this, and 8. That bar is the mathematical symbol for divisible, meaning 8 divides in evenly. So if I want to say it's not divisible, then I put a little slash through it like that. So that's not divisible by 8. So I told you, math people love symbols for everything because we're fundamentally lazy. Okay, so we love symbols. So 15 is not divisible by 8. So is this a valid identification number? The answer is no. And the reason why is because 15 is not divisible by 8. Yes?
To be clear, you could not do 7,125 divided by 8. It has to be the sum of.
It's the sum. The rule is the sum of the 4 digits.
Okay.
It's not the digits themselves. That is a great distinction because another one of these simple codes we're going to use does involve the digits themselves and not the sum of them. So it's good to be able to distinguish between the two. Any other question? That is a great question. Appreciate it. All right, well, if you got one, great. Ask it. If not, B part. Is 6,503 a valid digit or a valid code here, a valid ID number? Okay, so again, I'm just going to take the 4 digits. The rule is the sum of all 4 digits has to be divisible by 8 for this to be a legal identification code. So 6 plus 5 plus 0 plus 3, that turns out to be 14. Is 14 divisible by 8? Nope, 8 does not go into 14. It leaves a remainder of 6. So again, is this a valid code? The answer is no, it is not. Please do the C question. And if you have anything you want to talk to me about, please do. So in this one, we have 7 plus 6 plus 3 plus 8. 7 plus 6 is 13. Plus 3 more is 16. Plus 8 is 24. Is 24 divisible by 8? Yes, it is. We finally got one. So is that a legitimate ID code in this system? Yes. So what we're looking at here, this is kind of like this, one of the simplest forms of what is the mathematical equivalent of a secret handshake. Okay, so we're making sure that these digits, so like your Polk state ID number, there is some, I do not know, I should actually find this out, it'd be a good application in this class. Your Polk state ID number is generated in such a way that when it's entered in, you would know if it's a legitimate Polk state ID or not. What that does is, first off, it helps with typos, but then it helps in case somebody makes one up, like a credit card number or any sort of long string of numbers is going to have a way to be able to check that is legitimate. And this is kind of the simplest example. So here's the next thing. We're going to do the same thing with a similar thing with the same rule, but this time instead of determining if a identification number is legitimate, we're going to make a legitimate one. So somebody in the club says, hey, I want my first 3 digits to be 763. So I want to know what is my 4th digit. Remember, we can use 0 through 8. So here's how you're going to figure this out. This is, to me, the most straightforward way. We're going to take 7 plus 6 plus 3 plus x. And I want that to be congruent to 0 mod 8. Remember, what does congruence mean? Congruence from the last section means that there's no remainder. Or excuse me, congruence means what the remainder is. So this is saying has a remainder of 0 mod 8. So I've just written it mathematically. So 7 plus 6 is 13, plus 3 is 16. Now, at this point, you have an option. If you are savvy with your arithmetic and you can figure out just by looking at it what is divisible by 8, then great, you can write down the answer. If not, then this is an example of a problem we did in class last section. We treated this like an equation and we subtracted the 16 from both sides and then figured out what congruence class it was in. Okay, this one turns out, my example, I wanted to make my example the quote unquote more difficult one. My example actually has 2 answers because in our rule, notice we were allowed to use the digits 0 through 8. Okay, so pay attention to what the legal digits are. If I had said the legal digits were 0 through 7, the answer would be different. But notice 0 works because what's 16 plus 0? No trick questions. 16 plus 0 is, yes, just making sure you're awake, everybody. It's 16. Is 16 divisible by 8? Yes, so x could be 0, or what's 16 plus 8? 16 plus 8 is 24. Is 24 divisible by 8? Yes. So there are actually 2 legitimate digits that could be used to make a code. Okay, so I just gave myself the one where we had 2 answers just so that you would see most of the problems are going to only have 1 for you to do. Yes?
What is the digit set?
If I said up here in the rule that we only are using the digits 0 through 7, then there would only be 1 answer, and that would be 0. Okay, because 7 would not be a legal digit. Okay, great, good question. All right, so the E problem. Oh, hang on. Yes. Okay, yeah, this is a really good question. So the reason it's a mod 8 system is because we're dividing by 8. But I understand your question because you're like, hey, Perkster, last time you told us if it was a mod 8 system, we only used 0 through 7. So in the modular system, you're right. The digits are only 0 through 7 and then they repeat. But that's why the rule was defined here that we can use 8 because we're talking about regular numbers, not technically only a modular system. Okay. Yes, for check digits and codes, we care what we're dividing by. That's the key. Yes, beautiful questions. I love that you're processing these things. It's wonderful. Do the E problem. So this one, I'm going to take the 1 plus the 5 plus the 4 plus the x. I want that to have no remainder when I divide by 8. So that is 10 plus x. Now, again, I am sure most, if not all of you, could right now tell me what the x is that makes that divisible by 8. But I just want to, in case you can't, or in case you encounter some weird numbers, I just want to show you, remind you the process from last time. So I didn't do this in the previous problem because these are just the two different sides of the same coin. So what you can do is you can say, okay, I've got 10 plus x is congruent to 0. I'm going to subtract 10. And I get that x has to be congruent to -10. And then remember the way we determined numbers in the same congruence class is then we said, okay, it repeats every 8. So the next one, when I add 8 to this, I would get -2. Well, -2 is not one of my digits 0 through 8, so I got to do it again. When I add 8 again, I get 6. And 6 is from 0 to 8, so that is the value of x, would be 6. Okay, so example 2, if you got a question, please ask. You're doing great with that today, so wonderful. Example 2 says this. This is the same sort of thing. I've just changed the rule just to make it, to hold your interest 5 more minutes. Okay, so suppose that a 4-digit code is created for each person in a group so that the 4th digit is assigned to make the sum of all 4 digits divisible by 7. Okay, so this time we're dividing by 7. But notice to the question that was asked before, we're not limiting ourselves to the modular 0 through 6. We are saying in this problem that I can use the digits 0 through 9. Okay, so what I would like you to do firstly is you can do the A and the B problem. A and B, are those valid numbers in this system? So I'm going to give you about a minute 15 seconds to see. So for the A problem, we've got 2 plus 2 plus 3 plus 4. 2 plus 2 is 4, plus 3 is 7, plus 4 is 11. Is 11 divisible by 7? Nope. So the answer to this one is that would not be a legitimate code according to this system. The next one is 3 plus 5 plus 2 plus 4. When I add that, 3 plus 5 is 8, plus 2 is 10, plus 4 is 14. Is 14 divisible by 7? Yes, it is. 14 is divisible by 7. That indeed is true. Goes 2 times. So this, yes, is a legitimate identification number. We doing okay? Anybody got any questions? Okay, so I just changed the rule just to keep things spicy. So do the C problem, please. What is the 4th digit that I would put on there to make that a valid identification number in this system where the sum of the 4 numbers has to be divisible by 7? So this first problem is 2 plus 6 plus 1 plus x. I want that to be divisible by 7, so it's congruent to 0 mod 7. So 2 plus 6 is 8, plus 1 is 9. Well, what number would x be so that it's divisible by 7? X would be what? 5, yes. 9 plus 5 is going to be 14, so x is going to be equal to 5. That is the digit that would make that a identification code. Anybody get something different that we need to talk about? All right, then one more with this rule. Just do the D problem. It's the same sort of thing. So this one, we've got 1 plus 5 plus 4 plus x. Again, that has to be congruent to 0 mod 7, meaning it has to be divisible by 7. So that is 10 plus x has to be divisible by 7. Well, what's the only value of x from 0 through 9? That will make that true. 4. That is true. Great. X is 4. All right, I've got one more example of this type of rule. Okay, again, this is the simplest. Simple doesn't mean easy, but this is the simplest type of system to create some sort of identification code. And so the last one we're going to do is, instead of 4 digits, it's going to be 5 digits. Okay, so suppose that a 5-digit code is created so that the 5th digit is assigned to make the sum of all 5 digits divisible by 9. Okay, so there's 5 digits. This time it's divisible by 9. We're using the numbers 0 through 9. So go ahead and give this problem a try, please. Or the A and the B. You can do both of them. They're the same, basically the same problem. Okay, so part A, 73863, is this a legitimate one? My digits add up to 27. Does that make this a valid code?
Yeah.
Yes, it's divisible by 9. 27 divided by 9 is 3. So that one's yes. Great. Then the next one, the digits add up to 17. Is that a legitimate ID code?
No.
No, because that is not divisible by 9. So that one is a no. Okay, so then just like we were doing previously, let's go ahead and do the C problem. What would the fifth number have to be to make that a valid 5-digit code? Remember, we can use the numbers 0 through 9. So this one, I've got the number 7 plus 6 plus 1 plus 0 plus x. That's got to be congruent to 0 mod 9. So that's 13. 14 plus x is congruent to 0. Again, I'm sure most of you can look at this and say, okay, what number? In case you can't, I just want to make sure that everybody feels comfortable. So the way you would do this mathematically is I'm going to subtract 14 and say x has to be in the same congruence class as negative 14. And then what I'm going to do is I'm going to add 9 because that's the modulus. I'm going to add 9 to that until I get something from 0 to 9. So when I add 9 to this once, I get negative 5. When I add 9 to this again, I get 4, which if you didn't do that, you saw over here 14 plus 4 is 18. 18 is divisible by 9. Either way, that's the last value. All right, so we're just going to do one more of these. I know I got 2 more examples, but only one more is necessary. I think we've about exhausted the fun here. So just do the D part to the problem, please. Okay, so I added up the numbers, the 3 plus 4 plus 8 plus 1 plus x. That has to be congruent to 0, meaning it has a remainder of 0 mod 9. So that is 16 plus x has a remainder of 0 mod 9. And so then what's the only value of x that will fit and make that divisible by 9? Everybody tracking? We doing okay? All right, I'm doing great. So hope you are too. So an application of this that gets a little more complicated is with UPC code. So UPC codes, we're used to them. They're on everything. These bars contain information, 12 digits of information. Yeah.
You said you could use 0 through 9 for your digits, so technically each of 9 to 16 you get 27.
9 and 16 is 25.
I can't do math. Thank you.
That's
so
okay.
much.
That's why let's use calculators. Okay, so these bars, like when you go to Target and scan this, these bars contain the 12 digits that are the UPC code. And so what happens then is the Target computers look up that number in the database and then tells the price. Okay, so in order to avoid typos and being charged the wrong thing, there is a specific way that UPC codes are made. And so, I mean, you can see them everywhere. Here is a pack of staples. You can see there's the UPC code. This UPC code will follow the following, it'll follow this thing right here. I'm drinking some sparkling water. I don't know if you can see it on here, and I might just spill it all over me, but there's my UPC code on this. They're everywhere. So how are they formed? Well, they're formed like this. So the last digit in your UPC code, so on the example on your page, it's the number 2. It's called the check digit. And the check digit is assigned to make sure that the UPC code obeys the following rules. So here's the rules. First rule, you add the digits that are in the odd numbered positions. So meaning the first digit, the third, the fifth, the seventh, the ninth, the 11th. Okay, the odd places. You add the digits in the odd numbered places and you multiply by 3. Secondly, you take the other digits, the ones in the even numbered places, meaning the 2nd, the 4th, the 6th, the 8th, the 10th, and the 12th. You take those and you just leave them. You add up those digits and you add that to the result. You don't multiply by anything. Then you find the result mod 10. So when you do this, when you do these two things, if you have a valid UPC code, it should be congruent to 0 mod 10, meaning it should be divisible by 10. If it's not divisible by 10, then you've entered the information wrong or you've created a bad UPC code. So the third thing says find the result mod 10. Meaning find the remainder. If the result's not 0, then this is just the process we've done. I'll walk you through that when we get there. So here's my example 4. I'm going to slide this up. What we're going to do is we are going to find the check digit for the following UPC code. So we've got 11 digits. I want to know what's the last digit here that's going to make this legit. So what we're going to do first is we're going to take the numbers that are in the odd places and we're going to multiply them by 3. So just so that we all know, yes. Yes, the check digit is one of the digits, yes. Okay, so here we go. So I'm going to multiply by 3 times the digits that are in the odd numbered places. So help me out. This is I want to make sure that you're looking in the right place. What's the first number in an odd numbered place? 0. Yeah, I'm just going to put a little blue dot. 0. Plus, what's the next one? 3. Plus the next one? 4. And then 0. And then 8. And then one more. 7. Okay, there should be 6 digits there. The first, the third, the fifth, the 7th, the 9th, the 11th. Everybody with me so far? So far. You got this. You got this. No problem. Okay, now what we're going to do is we're going to add to that the numbers that are in the even position. So those are the ones that don't have the dot in my example here. So that is 2 plus 5 plus 1 plus 4 plus 0 plus x. The check digit is included. And when I combine all that, that should be congruent to 0 mod 10, meaning when I divide by 10, it has a remainder of 0. That's what congruent to 0 means. I've repeated that a lot because I know that's goofy and I want you to remember it. So now this is just calculator stuff. I'm going to do the first bit here. 7 plus 8 is 15, plus 4 is 19, plus 3 is 22, and 22 times 3 is 66. Everybody with me on where I got that from? If you don't see where any of these numbers are coming from, let me know. Yes. The times 3 is the rule. Step 1 of the rules. You add the digits in the odd positions, and then you multiply by 3. Okay, yeah, that's given to us. Great question. In the other parentheses, 2 plus 5 is 7, plus 1 is 8, plus 4 is 12, plus x. 66 plus 12 is 78. Again, you can go through our process of solving that and finding out what congruence class that's in, but I am 95% sure we all can figure this out. What number, there's only one, what value does x have to be in order for this to be divisible by 10? Has to be 2, right? That's going to make 80. 80 is divisible by 10. Okay, so x has to equal 2. That's the check digit. So far, so good? All right, then please do the same thing for the number right below. I've given you the first 11 digits. Figure out the 12th digit to make that a valid UPC. Yeah.
So I get like the number when you multiply by 3 and add them all together, and I would just divide it by 10, get the remainder, and do that 4th step, and I'm getting the same answer.
Exactly.
Okay.
Yep. You'll be happy to know that I just double checked my box of staples here, and I confirmed that the check digit is indeed 9, so it still works. Math is glorious.
Does that mean you can see operate on the same principles?
Yep, the UPC codes operate. Now, I would like to know, I've been meaning to check out like what ISBN, the code on the back of books, how it operates. I know credit cards, same thing, but they're a little tight-fisted with theirs because they don't want you making up legitimate credit card numbers, you know. Then you can call Amazon, or I guess you don't really call Amazon, but whatever. So you get the point. Like if you could make up your own credit card numbers, you'd use it. All right, so here goes. Let's get started. Check your arithmetic with mine. 3 times the sum of the digits in the odd places, and the odd places are 0, plus 1, plus 9, plus another 9, 4, and 9. Then plus the numbers in the even positions, so that's 4 and 5 and 4. and then 0 and 7 and x. And that has to be congruent to 0 when I divide by 10. So in the parentheses, I've got 9 and 4 is 13, plus 9 is 22, plus 9 more is 31, that's 32. So that is 96 if I've done my arithmetic right. Don't be afraid to correct me, because I do my arithmetic wrong all the time. And then I've got 4 plus 5 is 9, 13, that's 20, plus x. That needs to be divisible by 10. 96 and 20 is 116. And again, what is the only value from 0 through 9 that when I put it in there will give me a number divisible by 10? 4. Perfect. 116 plus 4 will be 120, and 120 is divisible by 10. Just a quick check. Any number divisible by 10 has to end in what? 0. Yeah, that's how we can hopefully get that pretty quickly. We doing all right? All right, then let's flip the page. Just for kicks, we're going to do one of these where we have to solve for the odd positions. So in this case, for some reason, I'm missing the third digit. So let's go ahead. I'm going to work this one with you. So here goes. So I'm going to set it up the same way we just set up the other one. I'm going to do 3 times the sum of the odd digits, which is 2 plus x plus 0 plus 3. 2x, 0, 3. And then 4 and 7. Then the sum of the digits in the even places, which is 8 and 5 and 1 and 0. And then, so 8, 5, 1, 0, and then 6 and 0. And again, that has to be congruent to 0 mod 10. Okay, so in my first parentheses, I've got 3 times x plus, that's 2, plus 3 is 5, plus 4 is 9, plus 7 is 16. And then in the other parentheses, 8 and 5 is 13, plus 1 is 14, plus 6 is 20. The distributive property, hope you're comfortable with the distributive property. I've got to multiply this 3 times everything in the parentheses. So that gives me 3 times x. What's 3 times x going to be? 3x. What's the 3 times the 16 going to be? Perfect. I'm going to add the 48 and the 20. And so here's what I end up with. I end up with 3x plus 68 has to be congruent to 0 mod 10. Now, if you want, if you don't feel like doing what we did the last section, you're welcome to fiddle around with the numbers and plug in numbers from 0 through 9 until you get the one that works. But what I'm going to do is I'm going to do the process that we were doing before, and I'm just going to go ahead and bring the 68 over, and then I need to find a number that's going to be divisible by 3 on the other side. So that's going to take just a second. So here we go. I've got 3x. I'm going to subtract the 68 and get 3x has to be congruent to negative 68. So, I mean, if you have a calculator handy, it makes the process a little easier. So you've got negative 68. 3 doesn't go into negative 68, as we all know. Okay, so what I'm going to do is I'm going to add 10 to that until I get something that does. So I'm just going to use my calculator here, and let's see, where is it? Here's my calculator. So we'll zero this out. We'll hope that no awkward texts come from my wife. So here goes. So here's 68, negative 68. So I'm just going to add 10 until I get something that's divisible by 3. So I'm going to add 10 to this. And when I add 10, I get negative 58. That's not divisible by 3. I'm going to add 10 again. I'm getting 48. Oh, that's divisible by 3. Okay, so negative 48 will be. So I got 3x is congruent to negative 48. And when I divide both sides by 3, when you divide negative 48 by 3, you get negative 16. And again, negative 16 is not a number from 0 through 9. And so I just need to know what congruence class is this in. And so you add 10 to this. So I'm going to take that negative 16 and I'm going to add 10 to it until I figure out what the congruence class. So I add 10, I get negative 6. That's not quite right. So I add 10 again, I get 4. There it is. That's the one. And so X is the value of X that makes that a legitimate UPC code is 4. Again, if you prefer, I mean, I really don't care. I just want you to do something that's going to work for you. If you don't like what I did right here, if you just would like to say, okay, I'm just going to plug in values of X until I figure out where it is, that's fine. You know, you plug in 0, you plug in 1, you plug in 2, you'll eventually get there. Just take you a little longer. All right, so one more of these, and then we've got one more one more rule that we're going to investigate, and then we'll be done with our supplement to modular arithmetic. All right, so I'm going to get started on this. You're probably still working. Keep working. So this time my digit is in the 5th spot. So once again, I'm going to take 3 times all the sum of the ones in the odd positions. So that's going to be 3 and 1 and X and 1. So 3 and 1 and X and 1, and then 0 and 2. And then I'm going to add up the ones in the even positions. So that's 5 and 4 and 7 and 3. 5, 4, 7, 3, and then 4, 2. That has to be congruent to 0 mod 10. All right, so that's the heavy lifting right there. The rest of this is just busy work. So I've got 3 times X plus 3 plus 1 is 4, plus 1 is 5, plus 2 is 7. In the other parentheses, 5 plus 4 is 9, plus 7 is 16, plus 3 is 19, 23, 25. I'm going to distribute the 3, and I get 3x plus 21. So here we are at long last. I've got 3x plus 46 has to be congruent to 0. I'm going to stop here because I just did a lot of arithmetic really fast. Everybody with me on my arithmetic? We doing okay? I know this is goofy stuff and there's busy work involved, so don't be shy about asking questions. Okay, so again, you're welcome at this point to just plug in repeated values of X to figure out which one gives you one divisible by 10. I'm just going to do this. I'm going to say 3x has to be congruent to negative 46. I'm now going to add the modulus, which is 10 to that. So 46 negative. So when I add 10 to that, okay, that's not divisible. Oh, no, negative 36 is divisible by 3. So 3x is got to be in the same congruence class as negative 36. That means x, when I divide both sides by 3, is same thing as negative 12. So divide that by 3. Whoops. What did I? Oh, there. Oh, I did it. Look at me. Oh. Now I'm goofing up. Slow down. There we go. Okay, now I'm going to add 10 to it. And when I add 10 to it, I get -2. I'm going to add 10 again. I get 8. So the digit that checks that out is 8. So again, if you were over here, 3 times 8 is 24. 24 plus 46 is 70. 70 is divisible by 10. There you go. That's UPC codes in brief. All right, we've got one more system that we're going to go through in this class. Okay, so we're just trying to keep it simple. We're doing a quick overview. The first system was the type of system where you just added up all the digits you were given and determined, is it divisible by something? The second one was a little bit more complicated version of that, the UPCs. The third one doesn't involve the sum of the digits. So the question was asked earlier, do I add the digits or do I just use them as they stand? And for the previous system, we used them, we added them up. But this time we're doing what's called a check digit scheme. Okay, that's what this is called, a check digit scheme. So this is called a mod 7 scheme. And I will make this a little simpler, but here's the formal definition. In a mod 7 check digit scheme for an identification number, here's our number. It can have any number of digits. That's what this goofy notation says. I start with my first digit, go all the way to my nth digit, however many I have. The last digit is called the check digit. And it is the smallest positive number that is congruent, meaning has the same remainder as the other digits. Now I know that's kind of goofy with all the notation. So if you don't quite got that, that's okay. Let's do this example. I'm going to show you exactly what's going on. So for example 6a, it says calculate the check digit for the number 1246x. We're in a mod 7 scheme. So the mod 7 scheme says this. This is exactly what it says. The 1246, don't add up those digits, just write them down. 1246. That has to be congruent to the last digit, whatever it is. Mod 7. So that means the first digits are in the same congruence class as the last digit. Mod 7. So the way I'm going to figure out what that is I'm going to take the 1246, I'm going to divide it by 7 and see what the remainder is, and to see what congruence class it's in. So 1246 divided by 7. 7 goes into 12 once, leaves me 5. Bring down the 4. 7 goes into 54. 7 times 7 is 49. Leaves me 5. Bring down the 6. 7 goes into 56 8 times. So I have 0 remainder. So what that means is the check digit that for this is 0. It's whatever this remainder is right here is your check digit. So that is 12460. The last digit of the number is the remainder when you divide by 7 of all the rest of the digits. We're not adding the digits up like we did previously. We're just dividing. What we're doing is we're just cracking off that last digit, the x, and we're saying, okay, all the digits to the left of that last digit, when I divide by 7, will have the same remainder. All right, well, we're going to practice this a few times because, again, I know this is goofy stuff. So try the B problem. See if you can determine what the check digit for that one is. Okay, so the check digit scheme just says this in this number. I'm going to separate it. I'm going to have the 3725 on one side, and it has to be congruent to X. So 3725 has to be congruent to X. Congruence means that they have the same remainder. So I'm just going to check out the 3,725. I didn't really leave myself a lot of room for the work, so I apologize for my bad planning. 7 goes into 37 5 times. Bring down the 2. 7 goes into 22 3 times. Bring down the 5. 7 goes into 15 twice. Remainder 1. So I'm done. So that means, what is the check digit? The check digit is the number that is the congruence class of 3,725. So it's 1. So the number here is 3725, and then the last digit is 1. Just so we feel real good about it, do the C problem. One more. Okay, so this one, it's a slightly longer number. It doesn't matter. It could be 50 digits long. It's the same thing. This last digit right here is the remainder when all the other digits are divided by 7. So I'm going to take the 2, 3, 4, 6, 1. Just going to come over here where I have a little more room, and I'm going to divide the 2, 3, 4, 6, 1 by 7. And whatever the remainder is the congruence class, and that is the check digit. Okay, so here goes. 7 goes into 23 3 times. Bring down the 4. 7 goes into 24 3 times. Bring down the 6. 7 goes into 36 5 times. Bring down the 1. 7 goes into 11 once. And leaves me a remainder of 4. So the congruence class of 2, 3, 4, 6, 1, the congruence class is 4. So that's the last digit. So this ID code would be 2, 3, 4, 6, 1, 4. All right, last thing for the day. You've done good endurance. Any questions you have, ask them. I'm just changing the scheme just a little bit. Instead of a mod 7, it's a mod 9 scheme. Okay, it functions the same way, meaning the last digit is going to be the congruence class when you divide by 9. So go ahead and do the A problem. What's the check digit for 1746X in a mod 9 system? So I'm going to take the 1746. I'm going to divide it by 9. 9 goes into 17 once, leaves me 8. Bring down the 4. 9 goes into 84 9 times. Remainder 3. Bring down the 6. 9 goes into 36 4 times, leaves me a remainder 0. So that means it's in the congruence class of 0. 9 divided evenly into 1,746. So the identification code is 17460 is the check digit, the congruence class. Please do the same thing for the next problem, the B problem. So I've got 13247. I'm going to divide it by 9, see what congruence class it's in. So 9 goes into 13 once, leaves me 4. Bring down the 2. 9 goes into 42. Let's say that's going to be 4 times. That's 36. That leaves me a remainder of 6. Bring down the 4. 9 goes into 64 7 times. Leaves me a remainder of 1. Bring down the 7. 9 goes into 17 once. And that leaves me a remainder of 8. So the congruence class is 8. So the check digit is 13247 that remainder. Still doing okay? Yeah.
Could we just put 8, or do you want us to write out the whole number on the test?
Oh man, make it worth it. Write out the whole number. Okay, one more of these and then we'll finish with a flourish. So please do C. And then we'll talk about what can we do if the if we know the check digit but we don't know the rest. So I divided the 9 into all but the last digit. That last digit's the check digit. It's the congruence class. So when I did the division, as long as you agree with my division, my remainder was 6. So that makes the check digit 6. So in general, it becomes a very hard thing to do, like with a check digit scheme. It becomes a hard thing to do to figure out if you don't know one of the other digits. Okay. But when we have a mod 9 system, it's relatively easy because dividing by 9 has a special property. Okay, so this is the information that you need in order to do the last 2 problems. And I'm going to do the D part with you, then you'll do the E part, will be done for the day. But here is the information that we will rely on. This is a little bit of number theory for you. So I'm just going to put a little asterisk down here at the bottom, and it's this. And you might have known this. You might have had an arithmetic teacher at some point that told you this. If the sum of the digits, so when I add up all the digits, if the sum of the digits is divisible by 9, then the entire number is divisible by 9. So just repeating that, when I add up all the digits of any number, if when I add up the digits, I can divide 9 evenly into that, then 9 went into the number. So for instance, I mean, if you grab your calculator, 333. 9, I guarantee you 9 divides into 333 because 3 plus 3 plus 3 is 9. So that's that. Here's another number. Let's say I have 1, 5, 3, 8, 7. What's that? 15. That's 18, 19, that's 24, 3. 9 divides into that number because when I add up the digits, it's divisible by 9. You can check me on the calculator. Okay, that's the property, and we're going to use that. Some other numbers have fun little ways to check if they're divisible, but nines is like the most fun. So how we're going to use that is right here with this number. So I know the check digit is 3. So what that tells me here is 125x is congruent to 3 mod 9. Because remember that 3, that is the remainder when I divide by 9. That's the congruence class. Okay, well then I'd have to go through and I'd have to check 10 values of x and see what you get when divisible by 9. That's one way you could do this. But the easier way to do this is like this. I know that this side, when I divide by 9, will have a remainder depending on what the sum is. That's what this property down here says. So what I'm going to do is I'm going to add up the digits. So 1 plus 2 plus 5 plus x needs to be congruent to 3. Because if the sum of the digits is divisible by 9, another thing you could say is if when I divide by 9, I have a remainder of 3, then when I add up the digits, the remainder will be 3. It's always going to work that way. It's the same. So I've got 1 plus 2 is 3, plus 5 is 8. I'm going to subtract the 8 from both sides. And I get x is in the same congruence class as -5. And when I add 9 to that, when I go one full cycle around the congruence class, I get x is the same thing as 4. That would be the missing digit to that number. It would be 4. So it's 1, 2, 5, 4, 3. And all that reply, we couldn't do this for a mod 7 or a mod 5 scheme. It all relies on that, our ability to just be able to add up the digits and divide into the sum of the digits. So real quick, I'll give you a minute and a half. Do the same thing with the e part. Figure out what that value of x needs to be by taking advantage of this property of dividing by 9. Oh, yeah. When I add all 5 digits up, it adds to 15. Right. And that's fine. But remember, the way this works is I divide 9 into just the first 4 digits. So, and then the 3 is the congruence class. That's how the check digit system works. And so we were given the congruence class on this one. So we need to figure out what value of x made 1,250 something have a remainder of 3. Mm-hmm. This one, the E problem, is congruent to 1 because the last digit, the check digit on this one is a 1. Okay, so it's always the way a check digit scheme works is you just break the number right there. You break off the last one. The last one's always the congruence class. And you divide into the other ones. And so in the special instance of 9, I can then add up the numbers because it's going to have the same remainder as the original number did. Okay, 9's the only one that we can do this for. That's why I changed the modulus to 9. You notice when we did the mod 7 scheme up here, I didn't ask you about a number that was not the last one because you need a computer to do it. It's very hard. Okay, so only with 9 is this a doable problem for us. Okay, so here we go. I've got my 3x54. I need to know what value of x would give me a remainder of 1 on this 4-digit number when I divide by 9. And you can go ahead and do what math people call the brute force method of just substituting 0 and then 1 and then using your calculator. You'll get there eventually. But what I'm going to do is I'm going to take advantage of the fact that if this number has a remainder of 1 when I divide by 9, then when I add up the digits, that'll have a remainder of 1 when I divide by 9. That's what this says right here. That's the little principle I gave you. So I'm going to have 3 plus x plus 5 plus 4 is congruent to 1. So 5 and 4 is 9 plus 3 is 12. When I subtract the 12 from both sides, let me squeeze that in right here. I didn't really leave myself a good amount of room, so bad professoring today. 1 minus 12 is negative 11. And now when I add 9 to that, negative 11 plus 9 is negative 2. I need to go again. Negative 2 plus 9 is equal to 7. So the number that makes this a valid check digit is 7. So 37541 would be the valid code. So you'll notice on the last page, there are some, or the second to last page, there's a page of homework problems. There's 11 homework problems for you to do. The answers to those problems are on the back. So none of this is in my math lab. The homework is right there. So if you have any questions, anything you couldn't